axiomatizing geometric construction. This is the title. Thanks again to Victor Pambuccian for his lecture. Victor, please.
Good morning. Today's lecture will be on axiomatizations of geometry in quantifier-free form with languages that contain no relation symbols. We'll go over a wide variety of axiomatizations, and we'll also talk about their significance, their philosophical meaning. So, on the one hand, we know that constructions have played a central role in geometry. For example, one can see that even Euclid's postulates were actually setting the scene for the possible constructions that can be performed. So it is bizarre that, given this central importance, all modern axiomatizations, until very late, were entirely in terms of relation symbols without any operation symbol. So in other words, if we think of Hilbert, for example, you have point line incidence, that's a relation. You have betweenness, that's a relation. You have segment congruence, same relation. You have angle congruence, but there is no single operation in there. So the language is one completely devoid of operation symbols. And one talks about constructions as a meta-mathematical thing, because Hilbert is interested in constructions. He mentions, ruler and segment transporter constructions, or dividers as they're called, as being weaker than ruler and compass constructions. So there is talk about constructions, but it doesn't happen in the formal language of the theory to be axiomatized. It's a talk that is outside of it. A major change came in 1968 when Nancy Moeller and Patrick Supis published their quantifier-free axioms for constructive plane geometry in Compositio Mathematica, in an issue dedicated to Aaron Halting on his 70th birthday. So the authors established a connection between their view and the more constructive view, more intuitionistic view of Aaron Halting. The language, though, in which it was made, the logic in which it was written was first order, so it was classical. There was no intuitionistic aspect in there. We will talk about genuinely intuitionistic axiomatizations next week. Now, the axiom system in the Moeller-Supis paper was for Euclidean geometry over Pythagorean ordered fields, which means the constructions that one can perform in this geometry are those of ruler and dividers. Dividers is a segment transport operation that allows one to take, let's see if I can do this here, allow one to take, where is this thing where you, oh, I know, okay. And we do it with the mouse. And no, we do it with this rather. And I can do a few things here, like I have a segment here and a ray here. And what I can do is to take this segment and lay it off here. So now you have this is congruent to that. So this is the segment transport operation. Okay. Okay, and we go back to mouse. Good. But now mouse is the wrong mouse. So I can only click this. I can click once more, right? And now I'm back to normal? No.
Click on the screen. Click on your slide.
On my slide? Then it's fine, okay. Now I have to do it this way. I can't do it this way anymore. Oh, I can still do it, okay. So, what's the language in which it was expressed? I'm not going to go into the individual axioms. That's not, I'm not going to go in any of the axiom systems into the individual axioms. So, the variables are just points in this axiom system. There are three individual constants. So you have some constant points that you start with. Because remember, there is no existential quantifier. So you can't say there exists A and B and C that do this. So you can think of this A0, A1, A2 as the Schoolemizing of that axiom that says there are 3 points. And there are 2 quaternary operation symbols, S and I. A0, A1, A3 are 3 non-collinear points, and that's what they will be all through this lecture, because you'll encounter them several more times every time they stand for the same thing, so I won't say that anymore. S of x, y, u, v is the following. So I have here UV, UV. I understand it as this ray. And I have somewhere an X and a Y. And it says that I can take the XY and lay it off here. So it comes somewhere here. No? That's what S does. S of x, y, u, v is this point. This point here is S of x, y, u, v. Okay? There need to be some conditions for this to make sense. Like, this should be an actual ray. In other words, u should be different from v. Or if u is v, then x should be y. Yeah, I can always transport a point to another point. It's going to be just a point where we transport. What happens when these conditions are not satisfied? Then it's an arbitrary point. In other words, the axioms don't mention anything in the case where these things don't happen. And this is all through the lecture. When I'm saying provided this or if this happens, if that doesn't happen, then that point or line or whatever the operation gives you is an arbitrary one. You can obviously arrange to have some arbitrarily chosen thing instead of saying, you can add an axiom saying, in the case where this doesn't happen, this is that. Say it's A0 or something. They didn't find any reason to do this effort to define it in the undefined cases because it just makes no geometric sense. You can do it. They didn't do it. I didn't do it later on. So it's going to be always this way. And I'm not going to mention arbitrary otherwise in all through this lecture. Now I have to go back to this, and click on this. I of x, y, u, v is the point of intersections of the lines x, y, and u, v, provided that these have an intersection. I'm sorry that it went below. So as a picture here, it's x, y, u, v. This is I of x, y, u, v. So the point of intersection of those two lines, provided that it exists. If it doesn't exist, it's an arbitrary point. Okay, so that's what the 1968 paper did. Oh, what's happening now? Oh, okay, good. A year earlier, Edwin England, in Algorithmic Properties of Structures, introduced an extension of quantifier-free first-order logic called algorithmic logic. This is extraordinarily important. What does it do? It allows, in addition to Boolean combinations of atoms, halting formulas for flowchart programs. I'm not going to go into the detail, but you can imagine a flowchart is kind of a graph where in every place you have either one thing going past or two. And you have basically the flowchart is telling you how an algorithm will go on. And a halting formula means that you have reached, I mean, it tells you that in this algorithm, it's either it ends at the first loop, or at the second, or at the third, or at the fourth, or and so on. So you will have an infinite disjunction of possibilities for your algorithm to end. So it's a quantifier-free formula in L omega 1 omega. Now, given some structure A in a language L, one can define the algorithmic theory of A as being all the algorithmic logic formulas of L that hold in it. Now, why is it extremely important? Why is the introduction of this algorithmic logic extremely important, in my view at least? Because if you look at the algorithm, at the Archimedean axiom, you might think it's a historical accident that, you know, the Greeks thought that you need to have something like this, and we're honoring the Greeks by giving it importance. But it turns out that actually it is extremely natural. If you think that the real numbers are natural, so you have some kind of continuum notion, and you ask the Cartesian plane over the real numbers, what is true in algorithmic logic? So in other words, suppose you are a traveler that goes to the Cartesian plane over the real numbers. And the only language you have is the language of Mohr-Mascheroni. You have these A0, A1, A2, you have S and I, and you're not allowed to use any quantifier. But you can use the halting formulas for flowcharts. So you go there, you see all the marbles that C2R has to offer, the Cartesian plane of real numbers. And when you come back to your own city, what are you going to tell them? You're going to tell them exactly the Mohr-Mascheroni axiom system together with the Archimedean axiom. That's the only additional thing that you will tell them because you have that. If you went on a trip to the same lands and you didn't have algorithmic logic, you just had first order logic without quantifiers, then all you could say is exactly Mohr-Mascheroni. So it shows you both that Euclidean geometry over Pythagorean ordered fields is a natural theory, and it shows you that the Archimedean axiom is a natural axiom. It's the only thing that algorithmic logic discerns out of continuity. So, what is the philosophical significance of the constructive axiomatizations? Because there will be lots of them coming. That's just the first one, right? The Mohr-Mascheroni. So why is it significant, this exercise, to constructively axiomatize geometries? And one of them is a return to geometries. Why? Well, we're told that, let's call these quantifier-free axiomatizations in languages without relationship symbols constructive. I hear already complaints that constructive is already occupied by intuitionistic, but for the purpose of this lecture, let's call these constructive. I use it because Mohr and Mascheroni call it so. No. Now, Proclus tells us
Victor,
yes.
When you say that in a language for construction you cannot use a relation, you are meaning that only monadic predicate are possible?
No predicate at all, except if you consider equality to be a predicate. But there is no other predicate at all.
Only function?
Only function symbols.
Ah, okay. Only function. Okay. Thank you.
You're not allowed to use any relation in that language if you want to consider that axiomatization constructive.
So in axiomatization, that is a construction must not have quantifiers and only function, no predicate.
Exactly.
Okay.
Obviously, you're allowed to have individual constants because those could be considered zero-array function symbols. Yeah?
Yes. Okay. Thank you very much.
You're welcome. So, what does Proclus tells us, which is probably the dominant Greek view of things? He says that a postulate prescribes what we constructor provide, that we constructor provide some simple or easily grasped object for the exhibition of a character, while an axiom asserts some inherent attribute that is known at once to one's auditors. So what we notice is that for the Greeks, postulate and axiom were not synonyms. They meant different things. So, again, we find something in the same clarification of the earlier quote. Just as a problem differs from a theorem. Remember, these are different things, a problem and theorem. So a postulate differs from an axiom, even though both of them are undemonstrated. The one is assumed because it is easy to construct, the other accepted because it is easy to know. Okay, so what does this whole thing mean? In current first order language, we're told that a postulate is a sentence that contains an existential quantifier. If you're talking in the traditional language with just relation symbols. In a traditional language with relations to symbols, a postulate tells you that something exists should other things happen. And an axiom is a universal sentence in that world with just relation symbols. It tells you that certain aspects of that relation are so, and they are easily visible, is what he says here. Yeah. So, and a problem and a theorem is the same thing. A problem asks for something to be constructed. A theorem asks for, if everything is there already on your page, it asks you for a certain relations to be the same, but it doesn't ask for a construction. So a problem is a theorem of your theory that has an existential quantifier somewhere. A theorem is a universal sentence in your theory. So postulates ask for the production, the poiesis of something not yet given, of a T, as every axiom, as every postulate in Euclid's thought is that there's T. Whereas axioms refer to the gnosis of a given, to insight into the validity of certain relationships that hold between given notions. In traditional axiomatizations that contain relation symbols and where axioms are not universal statements, such as Hilbert's, this ancient distinction is pretty much lost. Constructive axiomatics preserves this ancient distinctions. Why? Because the ancient postulates are precisely the primitive notions of the language. To put differently, you can think that we have schoolized our axiom system. The places that include that contain some existential quantifier have become now construction symbols. And the axioms of the Greeks are precisely our axioms. In fact, each one of our axioms is universal. So it's one of those, Greek axioms. So we have neatly separated the two. One of them are part of the language, and the other are all the axioms. Now, this is not possible all the time. In other words, there are geometric theories where you can't do this. So you can't turn every geometric theory into a constructive one. But during today's lecture, I will focus only on those where this can be done. So we're done with the first meaning. The first meaning is that we replicate an understanding of axiomatics that goes back to the ancient Greeks. The second meaning is that constructive axiomatization provides a rationale and a justification for various fragments of both Euclidean and hyperbolic geometry. What do I mean by fragments? Weaker theories. So in other words, theories where much more general models are allowed. And the question is, you can think that these are, pathological inventions for just some mathematical games that are being played. And the constructive axiomatization shows that that's not the case, that they're absolutely natural. All of these that occur, all of these that I study here, that have occurred in the literature in a non-constructive way, turn out to be exactly what a traveler to some standard thing can tell you if the language is restricted to a certain number of operations. And that shows that these theories are as natural as can be. So in this precisely definable manner, they're natural. So for example, as I said, in the Mohr-Mascheroni case, what does it show to be natural? It shows the geometry of ruler and dividers constructions to be natural. Because that's exactly what you can say when you go to the Cartesian plane of the real numbers about what you have seen. So the ordered Pythagorean fields are natural objects for this kind of, for geometry. This was not as surprising because you would say, oh, we knew that in Hilbert there was just an axiom telling you that you can lay out segments from one place to the other. But the fragments that we will encounter later on are much farther from obvious that there is a clear constructive meaning to them. Here's a short history of what followed after 67 and 68. First, there was a sequence of more papers by Erwin Engele on algorithmic constructions and algorithmic theories. And then in 1978, in a dissertation under the supervision of Wolfram Schwabhäuser in Stuttgart, it was in computer science because Wolfram Schwabhäuser was in a department of computer science. It provides an alternate axiomatization of the Euclidean geometry of ruler and segment constructions and segment transporter constructions. So in other words, for Mohr-Mascheroni, there were tiny, problems with the axiomatizations. There were certain cases that weren't treated, and so he fixed all that stuff. And provided also a constructive axiomatization for ruler and compass constructions in Euclidean geometry by adding another quaternary symbol C, which had the intuitive meaning of the intersection of a circle with a segment. Let's draw a little picture here, perhaps go back. I don't know. I don't see that then. Yeah, okay. So let's draw a circle here. And it's centered at X. So here is X in the middle. No, it doesn't look like X. So let's take this and do that. Okay, so after this X. Okay, so that's the center. And passing through Y. So here, say there is a Y. Okay. And here is a U, and here's a V. And what C does, it provides this intersection point here. Okay. And now, so it took 10 years for something, in the sense of geometric axiomatization, except for Engele's work, to come out. Then in 1983, a book by Engele came out, Metamathematik der Elementarmathematik, and in it, there's a whole chapter, chapter 2, that is about geometric constructions. And an important theorem is being proved that one cannot axiomatize geometry by any number of binary operations. even if you allow for the existential quantifier. Okay? So you cannot axiomatize in first order logic with any number of binary operations. That is not true in hyperbolic geometry. Hyperbolic geometry can be axiomatized with just the midpoint operation. So it's a specifically Euclidean property. Next came a sequence of papers by me, starting in 1989 and ending in 2003, which provide constructive axiomatization for a wide variety of geometries. There's a paper by Collapsible in 2003-2004, which provided an axiomatization for hyperbolic geometry. And that's about it for this type of axiomatization. There's a paper by Minkowski in 2010, which is strongly about geometric constructions, but it contains relation symbols, and it's done in intuitionistic logic. So I'll reserve that for the lecture on intuitionistic axiomatization. So before we go into these fragments, let's stop a bit as this oldest theorem about geometric constructions that was thought until 1928 to have been first proved by Mohr-Mascheroni in 1797. La geometria del compasso, that's right, the title. And then, through an accident, Yeltsin, walking into an old bookstore in Copenhagen, found a copy of Euclide's Danicus by Georg Mohr from 1672, in which Mohr had proved the same thing. The thing was that you can do with a compass alone all constructions that can be done with ruler and compass. In other words, that the ruler is not needed. So you would expect that all of these theorems that speak about constructibility itself have an equivalent in the constructive axiomatization. That is perhaps true, although it's not easy at all. Why? When you're axiomatizing in terms of these, you have to develop the whole geometry. When you're speaking about, can I construct with these, you know you're in that geometry. You assume all the properties of the geometry to prove that, this is that. In a constructive axiomatization, you need to develop the geometry in terms of the operation symbols. That's much more complicated. Moreover, many people who do constructions, in particular in hyperbolic geometry, choose convenient points where these two intersect. Well, how do you do that in constructive terms? You have to construct that point and make sure that it has the properties that you want it to have. And that is sometimes very difficult, or it wasn't done at all. But in this case, the answer is positive. So we know that for Mohr-Mascheroni, you need Archimedeanity. That's pretty clear. Why? Because what does the ruler do? The eye operation from Mohr and Sutis. That gives you the intersection of two lines, right? The intersection of two lines is a faraway operation. In other words, the result could be extraordinarily far. What can the compass do? It does only local things. In other words, if you give me two circles, let's say, what's their intersection going to be? Well, if the circles are on this whiteboard, then the intersection will be somewhere on the whiteboard. So it's a local operation. With a local operation, you can't get global points unless you have the Archimedean axiom that tells you that slowly local, many steps of local give you global. So the language contains a quaternary operation symbol, nu, and nu of A, B, C, D, and nu of C, D, A, B, denoting in arbitrary order the intersection points of the circles with centers A and C and radii A, B, and C, D, provided they exist. Let's draw a little picture here. So I have one circle and another circle, and these are centers A and C, and radii A, B, D, and C, D. Okay? So the 2 points here are this, and they're in any order. The axiom, there is no axiom that tells you it's this one, it's the lower or the upper. Both of them are, you know, as a set, they are considered as a couple. So you can axiomatize in algorithmic logic the whole of the geometry of Euclidean planes over Archimedean ordered Euclidean fields in algorithmic logic with this language. What are these Euclidean ordered fields? They're fields in which this is true. If x is bigger than 0, then there exists a y such that x is equal to y squared. So it means that every positive element has a square root. The Pythagorean ordered fields were telling you that the sum of two squares is always a square. So for all x and y, x squared plus y squared is equal to z squared. Those were the fields that corresponded to ruler and segment transporter constructions. These are the fields that correspond to ruler and compass constructions. And in this case, just compass constructions. So this thing is possible. You know? So the Mohr-Mascheroni thing, and this was done by me in 2003, going through the actual how do you do it. Okay. This needs to be here. Now, can we do something a little better? Can we had just one notion, this nu, but it was a quaternary one. Can we do better? Can we do just one notion that is binary? Obviously, one notion unary couldn't work at all, right? Because what operation is there on one point? What meaningful operation? Nothing. You can say an operation on one point gives you that point or a different point. There's nothing intelligent that you can do in that sense. But let's see if we can get just one notion with two arguments that does it everywhere. And actually in 1991, Zhang, Yang, and Hu have shown that a rusty compass is all one needs. What does that mean? Well, the Mohr-Mascheroni theorem told you that a compass is all one needs. But now even a rusty compass is good enough. What's a rusty compass? Oh, a compass that rusted. And what happens when it rusts? Well, you can't move this opening anymore. So you're stuck with one thing. One thing is just unit radius, right? Più uno più solo, right? So the axiomatizability over Archimedean ordered fields can be done inside algorithmic logic. With variable interpreting these points, you have two fixed points standing for two different points at a distance less than or equal to 2, and with one binary operation, epsilon, with epsilon of AB and BA representing the two intersections of the circles with centers A and B and radius 1. So how is this working? Let's see this. So I have 2 points, A and B. Why is it? I'm in the wrong place here. That's why it's wrong. Sheena? No, that's it. Okay. So now let's go a bit. Okay. And then let's go back here and get this. So I have A and B. Okay. And the circle with radius this, with center A and radius 1 is this, and the other one is now Goma. Okay. Perhaps that as well. Let's go back to. That's going to be fine. B was this. Now you do the circle. Okay. All these circles have radius 1. The intersections here and here, one is called epsilon of AB, and the other epsilon of BA. You don't know in which order, but that's all there is. With just this, you can axiomatize all of Euclidean geometry. Okay? Let's see. Oh, I need to go to the mouse. Okay, and then perhaps here's something. Okay. Now, what's happening in hyperbolic geometry with Mohr-Mascheroni? Julius Stromer, and in 1964, and Martinenko, a Ukrainian mathematician, in 1982, completely unaware that there was 1964, this paper by Stromer, which is an important journal, the Fels journal, or Journal für die reine und angewandte Mathematik, have shown that Mohr-Mascheroni holds in hyperbolic geometry. Why did this lead to something? Not yet. Victoria Klavita had tried for a while to write up these things, but then nothing came out, so there's nothing is published. What's the problem? The problem is this: in Stromer's case, he chooses these points that are convenient, and it's not clear how to do that in your language. And in Martinenko, I don't know exactly because I didn't go through it. My Russian isn't that great. So let's look at some other, let's look now at fragments. So far, there wasn't any fragments. I mean, ruler and compass is just a regular thing, and ruler and segment transporter, okay, you can consider it a fragment. But we're going to go now very deeply into fragments. And one way to go into fragments, I think, is by following the advice of no less than Voltaire. Voltaire tells us, je vous conseille de douter de tout, excepté que les trois angles d'un triangle sont égaux à 2 droits. So, let us doubt now everything except for the fact that the metric is Euclidean. In other words, the sum of the angles of a triangle is 2 rights. Okay, so what can one doubt then? So we can consider already that polar soup is did doubt something, namely the intersections of lines and circles, right? Because they had only the lines that were passing through the center of a circle were known to intersect that circle. Other lines were not known, and some of them don't necessarily. What if we doubt all line-circle intersections, as well as the order on a line and on a plane? In other words, what if we doubt order, free mobility, and the uniqueness of parallels? So you'd say that if you doubt the uniqueness of parallels, are you still in the les trois angles d'un triangle sont égaux à deux droits? Yes, we've seen this in the parallel postulate lecture, that the rectangle axiom, the fact that there exists a rectangle, is weaker than saying that there is just one parallel from a point to a line. So we remove free mobility. In other words, any line-circle intersection is gone. We remove order and we remove this. So what's left? Well, that's the geometry that we refer to as, this is a metric Euclidean geometry. And its origins go back to Friedrich Schur in 1909. Then it shows up in a paper by Bachmann and Reidenmeister in 1937, and by Reinhold Beer in 1944. The models, if we don't, this is, let's not doubt the uniqueness of parallels this time. Yeah. So for a while, let's just doubt order and free mobility, but let's stick to the uniqueness of parallels. So we're gonna systematically doubt things, and in the beginning, just doubt order and free mobility, but not the uniqueness of parallels. Then you get these kinds of things, the kinds of things that are called Euclidean planes in the literature. And they're made of what? Well, they're made of fields of characteristic different from two. So you have just a regular commutative field, and your points are just pairs of things in these elements of that field. So x1, x2, and you have a notion of segment congruence, and two segments are congruent, just as in usual, A minus B is C minus D. But the norm is in this funny way. There is this K here. So there is a K. Usually the K is 1, right? You're expecting the norm to be, you don't expect it to be this. You expect it to be square root of something, right? But our norm is to the square of the normal thing that you call a norm. But even that way, you're used to have here the K here. You used to have it 1. Well, -1, yeah, it's usually not in the squares of the field unless you have a field like complex numbers. But in the reals, for example, yeah, it's not. Well, here you're allowing any field and any K for which -K is not a square. And you can form for any such field and any such K, you can form this Euclidean plane. Why is it Euclidean? Well, because the metric is the usual one. There are rectangles, everything is nice. And there is a unique parallel from a point to a line. Two lines, this and this, are called orthogonal if and only if this happens. So this K again appears. Now, what's natural about these structures? They seem like an unusual thing. Why would you add this K? Just because you can do it algebraically? Well, no, it turns out that they're very natural. Why? Because you can axiomatize them constructively in a bisorted language with points and lines, and the three operations of phi, iota, and gamma. What does phi do? Phi of AB is the line that goes through A and B. Iota gives you the intersection point of two lines that intersect. If they don't intersect an arbitrary point as usual. And the same with phi. The A is equal to B, it gives you an arbitrary line. And gamma gives you, so it's an operation that has a point and a line as arguments, and it gives you the perpendicular raised in P on L. Whenever P is a point on L. When P is not a point on L, an arbitrary line. There's a variant of gamma that's called gamma prime that is called giving you the perpendicular drop from a point that's not on a line to that line. So in other words, gamma is the operation of raising a perpendicular. Gamma prime is the operation of dropping a perpendicular. Okay. Euclidean geometry, Euclidean planes correspond to the geometry of ruler and set square constructions. So the set square is something for which you can raise and drop perpendiculars. Here, we can only raise or only drop them. There are two types of set squares that we have, right? So the operations phi and iota correspond to ruler, right? Phi allows the operation that a ruler connects 2 points. Iota allows the operation of finding the intersection point of 2 lines. These are ruler operations. And gamma, or gamma prime, depending on preference, is the set square. One is just with raising, the other is just with dropping. You can also show that it's the same thing if you add an angle transporter. This is Helmut Schaefer that showed it, and I translated that into the constructive language. So what does this tell us? It tells us that why is it natural? Because if you go with this language, so suppose I have just this language, this L of this stuff here. Yeah? And I'm going with this language to the real numbers. And I'm asking, what can I say in this language about what I saw there? And then what I can say in this language, without quantifiers, obviously, that I saw there, is precisely this axiom system from 1998. So in other words, the geometry of these Euclidean planes that sounded funny, exactly that, to which you have to add axioms, statements corresponding to the fact that the sum of squares is never 0. So in other words, the formally real nature of the underlying field. This can be expressed in this language. The fact that the sum of the squares is not 0. If you consider that this statement is not that geometrically interesting, then you realize that these Euclidean planes that had this funny K and all that stuff is an actually very reasonable theory. It's natural. It's what you get when you go with this restrictive language to your familiar terrain, to the Euclidean geometry of the reals. Other axiomatizations of the same thing can be done with the two operations R and U. R is giving you the reflection. So if I have AB and C out here, then R of ABC is this, is the reflection of C in AB. Okay? If A is different from B, if A is equal to B, arbitrary. U of ABC gives you, if A, B, C are 3 non-collinear points, then it gives you the center of the circumscribed circle. This is U of ABC. Okay? So, again, if you go with these, just to these two, to the Cartesian plane of the real numbers, then you will end up with this axiom system that I don't mention, but that's the axiom system for Euclidean planes. Those are the funny K. And again, the axioms for formally real fields. The sum of squares is never zero. Okay? Now, the question is, do you need both of these notions? That's not known, although it's hard to believe that with U alone you can do anything. In other words, can you even define collinearity with U alone, even with quantifiers? I couldn't say how, but I couldn't prove that you need R. But you probably need both. U is clearly needed. Why? R is a local operation. In other words, if ABC are on the whiteboard, then R of ABC will be on the whiteboard. U of ABC is global. ABC may be on the whiteboard, and U of ABC is on the galaxy in Andromeda. Or even past the visible universe if we're in a non-Archimedean world. Yeah? So, this needs a little bit of help, and then it works. What if we doubt the uniqueness of the parallel from a point outside of the line to that line, but not order it or free mobility? Then you can do this with just two operations, T and N. N is the midpoint operation. And T is a segment transport operation that doesn't move to a different place. In other words, here is T. You have A, B, and say C here. So let's write these down, A, B, and C. And what this does is it, on ray AC, so think of this as a ray, it takes AB and lays it up here. So you get this point, so that this is the same as that. Yeah? So this point here will be called T of ABC. Yeah? So it allows you, so it's what is called a collapsible compass. Euclid, in his first proposition, shows that a collapsible compass can be replaced by a regular one. So this, you're allowed to do this only here. Yeah? So the difference between T and S, the operation of Mohr and Suppes, was that Mohr and Suppes allowed for this segment to be taken and moved somewhere else. We're not allowing this. The ray has to start from the same point. Yeah? You're just allowed this. So it's a kind of collapsible segment transport operation. Yeah? So, okay. So this theory of metric Euclidean geometry with free mobility and order first showed up in papers by Bachmann. Bachmann in 1949 investigated this particular theory in terms of constructions. He was interested in the Euclidean geometry of ruler, set square, and segment transport constructions, in which the ruler can be used in a very restrictive manner. You can only use it as a phi operation. In other words, you are allowed to join to get the joining line of two different points, but you're not allowed to use it in the iota operation. You're not allowed to use it for getting the intersection point of two lines. So what if I have just this ruler that allows you just to get the joining line and set square and segment transport? So the set square is used to both drop and raise perpendiculars. And you're allowed to use this segment transport, the SF operation of Mohr and Supes. It turns out that everything you've seen there can be done with the midpoint and the T operation. It is not known whether the midpoint operation is needed at all. It's clear that T is needed because the midpoint just gives you the A plus B over 2, and the T gives you something with a square root, so you'll never get that square root. But vice versa, could I construct the midpoint of a segment just by using T? It's not known. In 1948, Bachmann went further in this doubting process and doubted, in addition to order and free mobility, the intersection of non-parallel, non-orthogonal lines. So what do you get there? You get the so-called metric Euclidean planes. So now you have no more order, no more free mobility, and no more uniqueness of parallels. But at least you know that perpendicular lines always intersect. Okay? Then you get the metric Euclidean planes. And they can be axiomatized in terms of these notions. 3 points. The F, we found it already. The F, no, it's the first time we found it. The F is what? Is the foot of the perpendicular from AB to C. So from C to AB, sorry. Here is AB, here is C. The foot of the perpendicular from C to AB, this thing is called F of ABC, this point, yeah? And close. So that's that, and what is P? So P is this. You have A, B, C, and this is C, and it gives you the fourth point of the parallelogram, the fourth vertex of the parallelogram here. This thing here is P of A, B, C. So imagine A, B, and C being like this, right? Then P of ABC is the image of C under the translation that moves A into B. So that's P of ABC. So it works all the time. Yeah, it doesn't have cases in which you don't know. F of ABC, obviously, if A is equal to B, then you have nothing. Yeah? Because you're not interested in the perpendicular. Or A itself in the degenerate case. I define it in that way. So in the degenerate case, you consider that the perpendicular is just A from C to A, C being whatever. So none of them have non-defined cases. Again, the question is, do you need P? It's an open question. At the time, so in the 90s, I had a computer science friend and asked him to do these things, to start with some point, say 0, 0, 1, 0, and whatever else, and try to do the F operation, to drop perpendiculars surreptitiously, and see if you ever get the fourth point. And it went over, I don't know, some hundreds, thousands of things, and it never got it. But that doesn't mean that it's not possible, I don't know. And nobody I encountered thinks that we have any idea how to solve this problem. All axioms have at most 4 variables. We'll we'll see why this is important when we're going to talk about simple axiom systems. There's a theorem of Dana Scott in 1959 that says that every axiom system in terms of points for n-dimensional geometry has to have at least an axiom with n+2 variables. So for plane geometry, you can't do better than 4 variables. Oh, something happened. I'm still out. Okay, I need to go to mouse. And then a bit here. Okay. Well. Okay. Now, we doubt a little more. We're getting to the rectangular planes that were mentioned by Bachmann in 1959. What do we doubt here? So, in the metric Euclidean case, we doubted order and free mobility and the uniqueness of parallels. But we did not doubt that perpendicular lines intersect. Now we doubt even that. And the first example was provided by Bachmann in 59, and then they were introduced by Katzel and Stanik in 79 by a mixed group theoretic, geometric and group theoretic axiom system as a generalization of metric Euclidean planes where perpendicular lines need not intersect. A purely geometric axiomatization for these rectangular planes of characteristic different from 2 was provided by Rotraut-Stanik in 1984, and it was completely in terms of relations. The relations were incidence, typo there, incidence, parallelism, and congruence. Now, it turns out that they can actually be axiomatized in this language, where I don't need to explain to you any of these notions because you know them. P is the parallelogram thing, completing the parallelogram, and R is the reflection. So in other words, if I go to Euclidean planes with this language, so suppose I go to all Euclidean planes, those with the funny K, to all of them, and see what's true in this and that and that and so on. And then come back and say, well, here is what I've seen. And the thing that I'm going to tell you in this language is precisely the theory of rectangular planes. Again, it's not known if P is needed at all. So in other words, could you constructively axiomatize just with R? It's not known. What about absolute geometry? What's that? Well, now we depart with Voltaire. Voltaire told us to not to doubt the sum of the angles of the triangle. Now we get into much more doubtful position. We doubt even that. So we doubt the sum of the angles, we doubt the uniqueness of parallels, but we leave everything else put. In other words, free mobility is there, order is there. Then we get absolute geometry. In 2001, I could show that you could do this with, in a language, you can axiomatize it in a very interesting language that contains this T prime. T prime differs slightly from T. T did what? It moved this onto this. T prime moves it onto the other side of this point. So it does the same thing. It only the T moved it on the ray determined by these 2 points, and T prime moves it on this, away from this, right? On the opposite ray. So it's a segment transport operation that is local. And J is the point of intersection of the segments AB and CD. So AB, CD. Only in case they do intersect as segments. So this point here is J prime, AB, CD. Why prime? Well, because I had used J for something else in the paper, so. Okay, so this is absolutely remarkable. All of absolute geometry is only the story of T prime and J prime. So it speaks only about the intersection of segments and the ability to move a segment on a ray. This was possible only through the work of Gupta, who showed that the outer Pasch axiom can be proved from the inner Pasch axiom together with some metric axioms. Okay. Not yet. Something is, and now it's okay. So this shows that all ruler, set square, and segment transporter constructions in plane absolute geometry can be carried out by means of two geometric instruments, the segment transporter and the segment intersect. You don't need anything else. So, if you were to visit both the Euclidean plane over the reals at one time, and at another time, the hyperbolic geometry over the reals, and all you have at your disposal is this language with T prime and J prime, and the 3 points, and you're not allowed to use any quantifier, then, and you're asked to tell the common story of these two trips that you've taken, then the result will be exactly absolute geometry. Absolute geometry is a very natural thing if you believe that Euclidean geometry over the reals and hyperbolic geometry over the reals are natural models. Now, if we enlarge the language by another ternary operation, this ABC story, let me show you what it does. So, AC and B. So it gives you a point, this point here. This is A of ABC, the A coming from Aristotle, so that the perpendicular from here to here is precisely as long as this. So you're given 3 points ABC, right? These form an angle. I mean, if they don't form an angle, it doesn't give you anything interesting. It gives you a point that is arbitrary. Okay? But if they do form an angle, then it gives you the point on the ray AC, for which the length of the perpendicular is the same as the length of AB. Okay? So AB being arbitrary, this kind of tells you that the Aristotle's axiom is true, right? Because Aristotle's axiom told you that you can find a perpendicular like this that exceeds any given thing. Well, if you can make it equal and you go a little bit past it, then you're going to exceed it. So it's using the Aristotle's axiom as an operation, because this time it is exactly that amount, not greater, but exactly a given amount. With this, so if you add to the axiom system that we had before for absolute geometry, an axiom about A, namely this, that says this, then you obtain either Euclidean or hyperbolic. If you have to add another axiom saying that the metric is Euclidean or the metric is hyperbolic, And you get both of these geometries in a language with just A, T prime, and J prime. So you can axiomatize both Euclidean and hyperbolic geometry in this constructive language. Now let's get rid of this. No, it likes better this. Okay. Now, what about an even further doubting? In absolute geometry, we doubted the sum of the angles of the triangles, and we doubted the uniqueness of parabolas. But you can go further and doubt order and free mobility as well. And we've met these already in our first lecture. They're the metric planes of Arnold, Schmidt, and Bachmann. That can be, in traditional style, axiomatized by saying that there are 2 points. 2 different points are connected by exactly one line. Orthogonal lines are, orthogonality is symmetric, and orthogonal lines intersect. Through every point, there is a unique, to every line, there is a unique perpendicular. I'm talking here of the non-elliptic metric planes. Yeah, there's just one type of it. To every line, there is at least a reflection in that line. And the composition of reflections in 3 lines A, B, C, which have a perpendicular or a point in common, is another reflection in a line B. So this is not just the metric planes, it's the non-elliptic metric planes, because if you're saying that the perpendicular is unique, then you have excluded already the elliptic ones. Now, these that were expressed in that terminology can be constructively axiomatized in this language. The F we've already encountered. Well, who's the P now? Well, it's the so-called 4th reflection point. Well, what is that? It's better for me to draw it. I explained it there, but that's... Suppose I have an A, a B, and a C. Yeah? Let's raise perpendiculars here. Yeah? And let's think of the composition of the reflection in these 3 perpendiculars. These are 3 perpendiculars that have a common perpendicular. So according to the 3 reflections axiom, there must be this, the composition of the reflections in these 3 is another reflection in another line. Well, this line has an intersection point with the horizontal line. This thing is P of ABC. Okay? So let's get rid of this, and then here, and then do something here, and this is the explanation. Okay? Too long an explanation, better the picture. Okay, and oh, by the way, we don't know whether P is needed, by the way. In other words, is it enough to have just F? Is it enough to have just sigma? Who is sigma? Sigma is the reflection of B in A. It's P of ABA. Is it enough to have just this, F and sigma? Could you do it? Nobody knows. Is it enough to just, can you get out of FP? Again, nobody knows. Now we're done doubting. Let's move to fragments of hyperbolic geometry. So we've doubted all the way to these non-elliptic metric planes. Now we move on to fragments of hyperbolic geometry. The first of them would be the elementary hyperbolic geometry of Hilbert that told you in, we spoke about this last time. Here you have an L, here you have a P, and it says that there are two lines like this, R1, two rays like this, R1 and R2, that are parallel to the lower ones, and everything in between them intersects. Yeah? So these are, if you draw it on the Beltrami Cayley-Klein model, then if this is L and this is P, then the R1 and R2 are just joining P with the so-called ends. And everything in here intersects that. Yeah? Okay, so that's what it says. Well, great. So what can we do with this? Well, first of all, Handist, Stromer, Semyonovich, and Rautenberg showed that ruler and compass constructions in hyperbolic geometry can be achieved by a ruler that allows, in addition to the joining of points and intersection of lines, the drawing of the limiting hyperbolic parallel. So that inspired me to get a constructive axiomatization. And actually, it can be constructively axiomatized in a language with points and lines, with phi that we know already, iota that we know already, and two operations, P1 and P2. Well, what are those? You kind of imagine what they are, because we have two parallels, right? So if you have L and P, then P1, PL will be the one to here, and P2 will be this one. So this is this, and that is that. Yeah. So you have two operations, they're not distinguished, so you don't know which is left and which is right, in your axiomatics. And you can do it. So in other words, what does this show? It shows that Hilbert's elementary hyperbolic geometry is a natural theory. Because if I were to go with this language to the hyperbolic geometry over the reals, all I could say is exactly Hilbert's hyperbolic geometry. So that is a natural thing to do if you think that these operations are natural, which I think we ought to think, because that's the limiting parallel is a very geometric thing. So let's see how we can do this. Okay, then we move here. Now, in 2004, so I was wrong, I stopped in 2003, actually there's one more paper in 2004. There is a constructive axiom system for both hyperbolic and Euclidean geometry was provided with only ternary operations, 9 ternary operations. And each of these operations had absolute meaning. So there was none that was particularly Euclidean or particularly hyperbolic. And all the statements were of at most 4 points. Now, another axiomatization of hyperbolic geometry that I mentioned in the beginning came by Victoria Clavitus. And there you have points as variables. That you have 3 individual constants, A0, A1, A2, and the Lobachevsky function of the first 2 is P over 3. What is this Lobachevsky function? So we know that in hyperbolic geometry, there is something that's called the angle of parallelity. What does that mean? It means that when you have here a point P and you drop a perpendicular to a line L, then there is a certain angle here. Yeah? And one can show that the angle here depends only on the length of this, on the length of this perpendicular. So in other words, if you go to another line and another perpendicular, you're going to get the same angle. So if this is D here, This here is called capital P of D. Okay? So if you give me 2 points that are where the angle here is P over 3, in our case, yeah, P over 3, then I can do a lot better than usual. I need to erase all this thing. And here, and then something here. No. Okay. So you have one quaternary operation that gives you the point of intersections of 2 lines, provided that it exists. And 2 ternary operations that are the 2 segment construction of places. So let me draw a picture for this. You have an A and a B. AB. And you have a C somewhere. And what you do is you take AB and you lay it off on AC. You get one here and one there. So this is the same as this, is the same as this. And these 2 people are called epsilon 1 ABC. And this one is called epsilon 2 ABC. Obviously, you don't know which is which. Yeah? So it's a segment transport operation where you're agnostic about order. You can transport it in 2 ways. So you have these. So, okay, so there you have your segment transport operation, and that's enough. With this, you can do everything. So in other words, you can do everything means what? With just iota, A0, A1, A2, and the epsilon 1 and epsilon 2, you can axiomatize all of elementary hyperbolic geometry, which is remarkable because you don't have a circle continuity axiom. Remember the previous one, this one, had these P1 and P2 stories, right? Those are equivalent to circle intersections or circle point intersections. They give you something, limiting. So, because think about it, we're not talking about just the hyperbolic geometry of ruler and segment transporter instructions. This is going to be all of it. You can construct everything that you can construct with the compass as well. And your axioms, though, tell you nothing about that. You're using just these 2 operations. Why can you do such a thing? This is inspired by the work of Stroman in 62 and Gafurov in 65, who have shown that given a few points in convenient position, one can perform all ruler and compass constructions with just a ruler and a segment transport. Yeah, so in fact, Stromer had shown that if you have on your hyperbolic plane 2 hyperbolic parallel lines, then you can do it. And Gafurov has shown that if you have 2 points that have that Lobachevsky function P over 3, then you can construct the 2 parallel lines, so you can use the Stromer result. So this was all for full elementary hyperbolic geometry. Now, Klingenberg, in 1954, axiomatized in the group theoretical style of Bachmann, a theory whose models we will call generalized Kleinian models over arbitrary ordered fields. The Kleinian models, what I call Beltrami, Cayley, Klein, are the interior of the unit disk, but the field has to be Euclidean. In other words, any segment inside that circle will intersect the circumference. So in other words, there are the so-called ends that exist. Klingenberg created a hyperbolic geometry in which you have the essential hyperbolic metric is present, but the limiting parallels aren't. So in other words, you have the same interior of a unit circle, but this time the field is just any arbitrary orbit field. So many lines won't have intersections at all with this. There won't be ends. Now, is this a natural thing or is it just an invention of let's get it more general? The constructive axiomatization shows that it is a very natural thing. Why? Because you can axiomatize these in a bisorted first order language, so points and lines, in which you have phi, which we've met already, it's joining 2 points. You have iota, which we've met already. You have f, which we've met already, it's the foot of the perpendicular. We have p, which we've met already, is the 4th reflection point. You give me 3 points on a line, then I get the 4th reflection point. And the new operation zeta. Zeta gives you for 2 lines, G and H, their common perpendicular, should a common perpendicular exist. A common perpendicular exists very often in hyperbolic geometry. Why? Except for when 2 lines are hyperbolically parallel or intersect, 2 lines in hyperbolic geometry always have a common perpendicular. Okay? So, if I go now to the hyperbolic model over the reals with this language and ask what are all the things that I can say there, it's exactly the theory of Klingenberg, which shows us that it is a very natural theory. Again, one can ask for what is the hyperbolic geometry of restricted rulers. So again, ruler can be used only to join, but not to intersect, the way Bachmann did in his 49 paper. And set square and segment transport. Again, this can be axiomatized. And in a paper where I axiomatized this in 2003, I've also solved the problem from 1965 of Bachmann's, which asked for the exact description of these models, which is in that paper. I won't bother you with that. So again, is it a natural theory? Yes, because if you go to the standard hyperbolic plane of the reals with just this language, that's what you get. Now, there's an even further fragment of hyperbolic geometry that is called Treffgeradnebenen, which doesn't have a nice English translation, perhaps meeting line planes, where you do the following. You start with the Pythagorean field this time, right? So remember, in Klingenberg, you get just any ordered field. Now you have a Pythagorean field. And you have the unit circle. And you look at the points in your plane, which have the property that every line through them intersect the circle. You consider only those points to be points of your world, of your universe. And the lines are all the lines that pass through this. And else you keep your regular hyperbolic metric. The question is this any natural or is it a crazy thing to just, let's do something? It turns out that they're natural. Why? Because again, there is a constructive language, this one, in which you can axiomatize them. And moreover, if you go with this language to your standard hyperbolic plane, then that's what you get. What are these things? This is the put of the perpendicular from P to G, this perpendicular sign. The tau is a segment transport operation. The tau primes, yeah, it gives you two segments, just as very similar to the epsilons that we've had in the clavicle system. And the lambdas, these are the most important. These are, I need to draw them. So, drawing. So I take I have 2 points here, A, B, and there is a C somewhere, okay? Now let's do this. The lambdas are the two lines that are hyperbolically parallel to AB and perpendicular to AC, okay? So perpendicular to AC and hyperbolically parallel to this. So there's something like this. So here it's perpendicular, here it is parallel, okay? Provided that such a thing exists, it very often exists, unless these are perpendicular themselves, AB and AC, then it exists. So you have, what kind of instruments do we have then? Well, we have a set square because we can draw perpendiculars, we have a segment transporter, and we have this funny hyperbolic parallel and perpendicular draw. This funny thing, although it looks funny, it isn't so bad. It was actually introduced in 1962 by Al-Dahir, and it was called the hyperbolic ruler. And again, we've shown that it's natural, and that's the end of my talk. So even the treffgeraden Ebenen are very natural notions. So I hope I didn't take too long, because I didn't look at all of it.
Thanks. Valentin, please.
Well, I was just applauding, but since you allow me to to ask a question, let me ask one. Yeah, I had to miss some short parts of your lecture, so I'm not sure. But did you mention anywhere the origami constructions and axiomatization of origami?
Yes, there are papers also on origami constructions that I did. They're not that hard, yeah. You get the Vieta fields there. You get an extension of you can do more than with ruler and compass. But I tried to focus on this on fragments, and usually with origami you can get more. So I try to restrict the scope of the discussion. You know?
I understand. Thank you. Very nice lecture. I enjoyed it. Thank you.
Other questions? Okay, I have one. At the point you said that constructive axiomatics preserve the ancient Greek distinction between postulates and axioms, the problems and theorems. And this is a famous in the Proclus, this distinction is very famous Proclus and the others. But in contemporary times, many scholars criticize this distinction. At a certain extent, it's a cliché. Because you have in Euclid's optics, you have a problem as a sort of existential propositions, or for example, it was noted by Mohr, or Sidoli noted that we have to redefine the problems and the theorems in ancient times and so on. And in a certain sense, so if it is true, it is not natural. The constructive is not not appropriate axiomatization to capture this distinction, because this distinction is not real in this sense.
Well, you're right in the sense that, I mean, as I pointed out in the beginning, there are structures, for example, the translation structures of Johannes Andre, the Yeltsin plane, the affine planes, and many other structures, the Barbilian planes, the remoteness planes, where you can't do anything without relations in your language. So this is rather an exception. You can't say that we can do this to all geometry. In fact, it's a small slice of geometry where this can be done. So in that sense, you're absolutely right that we can't work with that distinction in all of mathematics. It would be crazy. It doesn't work. There are things that just don't work that way. But I think that to the extent that we can capture it and preserve it, it's perhaps another way of looking at things, the way we do an axiomatization in a group theoretic term, or with relations to compare it to others. The constructive axiomatizations are, whenever possible, I should be pursued, because they can preserve that aspect of that Geminis and Proclus told us that we should do it that way. You're absolutely right. It can't be kept even in ordered geometry. You're going into problems, because you can say, okay, what is constructive? Isn't this just some kind of schoolemization of things? I mean, you get these things. Well, yeah, but with schoolemization, you're now quantifier-free, but you still have your relations. So how can you get rid of relations? And mostly you can't. I mean, in most theories you can't. So to put it in this form, yeah, you can turn everything into quantifier-free, but the specific nature of these these operations is that they give you very specific points. It's not just kind of arbitrary somewhere. But for example, if you have just an ordered geometry, then you know that for any 2 points, there's a point in between or a point outside. But which one? I mean, there are many. And you can't really, the operation, your schoolemized thing, won't give you something exact. Whereas in all of these, it's very exact. And these will obviously be exceptions. In the big sea of geometry, they're rather an exception. But I think that when they are, perhaps the two go together, the justification of fragments and the Geminos thing. Because these postulates, which are in our case the language, determines the naturalness of the fragment. And yeah, you're right, you can't keep this through all of mathematics. It's usually the exception that it works to keep the distinction. And even with the distinction, it's very questionable if now our axioms are all so natural and so obvious. Yeah. So yeah, I can see the point that it won't work universally. I see that Vincenzo has a question.
Oh yes, thank you very much for your very interesting presentation, Victor. I have a specific question, a more general one. The specific one is about the rusty compass geometry. I would like to know something more about the interpretation of this kind of geometry. At first sight, it seems a sort of attempt to build topology from metric, if I can say. and the sense that a rusty compass, in a certain sense, establish only distances. And the attempt is to build a topology moving from distances. Is it the first question? Is this interpretation correct? And in which measure this is possible to do? It is possible to find topological relation moving from building on metric relation. This is the first question. The second one is more general, and I ask to you if this kind of geometric literature has been connected with many interesting philosophical problems. One of these is, for instance, the problem of knowing of the relation between knowing how and knowing that. It is possible to find in the construction some kind of knowledge that it is not reducible to knowing knowledge that, for instance, or on the contrary, all knowledge how that we know in construction, geometrical construction, can be represented in an axiomatic, and so in a knowing that form. This is a kind of problem. And other is someone has used this intermediate axiomatic system to investigate better perceptual space. We know that perceptual space is something very complex because it's a sort of mingling, a mixture of different kind of space, a sound space, a kinesthetic space, a visual space, and all this kind of space have a sort of geometry, and there is a sort of building of perceptual space based on this different perceptive space. And I read something about the possibility to find the formal structures that are able to build this kind of spaces, and to attempt to answer to the question, which is the geometry of sound space, which is the geometry of site space, which is the geometry of kinesthetic space, which is the geometry of the different levels of construction of spaces that we have in our perceptual world, which kind of structure are buried in our perception, and mathematical instrument can make explicit this structure. I wonder if there are literature of this kind of stuff. Thank you very much.
Yes, thank you for your questions. Let's see, I think I remember the first one is about the rusty compass and whether the metric defines topology, and I think you're right. And why are you right? Because who is the topology in elementary plane geometry? It's the betweenness relation. And the betweenness relation is definable in terms of that rusty compass without quantifiers. So that means that yes, we can get the topology out of the metric in that particular case. The second question was about knowing how and knowing that. And I think you can put it into, although it's more general than the Geminos definition of the distinction between the poiesis of something and the gnosis of something. I think it comes reasonably close. And your next question was about the different spaces, right? The higher dimension, you asked higher dimensional. I think all of this approach crumbles. It's a specifically two-dimensional one. In higher dimensions, you won't be able to do that. the constructive approach. The other question about the many other spaces of visual and sound and so on, I think if anyone knows anything in this audience, it's probably Val who knows something, because he has written about things like temporal and so on. So I'm the probably least knowledgeable person about that. So I can't give you a meaningful answer.
Thank you very much.
Other questions? I have another for you about Sealand 1978 papers. I think that the Sealand quadratic relation C was the first occurrence of this relation was in Freyes. And Freyes at a certain point wrote two papers for journal Scientia about the postulates of continuity. And one of them proposed this relation C as a relation inside Euclid. And the idea is the continuity Euclid is something known by Euclid, and his argument is connected to the presence of this relation. So I think that this is the first. And the question is if you know.
When was it? In the 50s or when?
Yes.
Because Freyes mostly wrote in the 50s. Yeah, in the 50s, these things were, I mean, yeah, it was known kind of that there are several ways in which you can put this circle line continuity, because this is the question here. One of the ways is this, that you have a circle and then you have a point inside and one outside, and this intersects, which is exactly what you were referring to. The other is the intersection of two circles.
Yes.
And the other one is the intersection of a line that has a point inside of a circle. So these are slightly different. It was shown by Stromer in 1972 or so that these are equivalent even in absolute geometry. The proof is very difficult. In Euclidean, it's easier, but in absolute, it is very complicated to show it. And at the time, I think as far as references, perhaps it's Tarski, but Tarski wrote in this Rand report, which wasn't very well read. I think there is something about it in 48 or so. And then in 59, which may be after Freyes, but definitely he's there in the beginning of these, of asking these kinds of questions. Yeah.
Thanks. Other questions? Okay. No questions. So thanks, Victor.
Okay.
And next lecture will be next Wednesday at the 11 o'clock. The argument will be impressionistic axiomatization of geometry in the direct proof of Steiner-Leibniz theorems. And thanks again, thanks to the audience, and see you next Wednesday.